Well, hello, my name's Craig Beasley, and I'm going to be talking to you today about wave equation receiver deghosting, and I'm giving this presentation on behalf of my co-authors Richard Coates and Cynthia Lapilli, and we're all at Western GECO, which is a part of Schlumberger. Well, for those of you old enough in the audience that have heard about receiver ghosts, you may have these images in your mind of when maybe you were young trying to watch television, and you would see double images on the television, and maybe you tried to account for this with a set of rabbit ears, or maybe something even more exotic like you see on the screen there. But the concept we're talking about today is exactly that one that we're familiar with in the video world. And so the idea of the ghost and how to deal with it has become quite important in the last few years. And so we'll talk about this in a little bit different context today than maybe you've seen in recent years. So just a few words on the history of this problem. I was surprised a little bit myself when I began to study this a little bit more to find out that the first work actually that I can find on deghosting was done by Van Melle and Weatherburn, colleagues at Shell. This was done actually just after the war in 1948 in Bel Air, Texas, and they published their results in Geophysics in 1953. So it's not an entirely new topic. Back then they were concerned about the source ghost, which we're really not going to talk about today, except until we get to the end of the talk, and then we'll mention it. But they had the idea of trying to do something about the source ghost by placing more than one source in the subsurface and delaying the timing of one source so that they tried to eliminate the part of the wave field that was causing the ghost reflection. Now, if you go on and study more about deghosting, you'll find that all the way through the 60s, the focus in deghosting in geophysics was on the source ghosts. And it wasn't really until marine came into its own in the 80s and 90s, let's say, that we began to worry about seriously attacking the receiver ghost in the marine data. And following on what Van Melle and Weatherburn did with two different source experiments, the first ideas, of course, were to try to attack it with more than one sensor. And since the early 2000s, this concept of multi-measurements with streamers has become the method of choice to approach the ghost in the acquisition systems. And of course, there have been processing attempts at removing the ghost, and we'll talk a little bit about that in a moment. So the way I characterize the modern approach to receiver deghosting, really there are three sort of streams of thought in trying to solve this. You can do it with acquisition, which is the preferred method. So as we saw, following on the notions of two sources, we have complementary receivers that have different ghost characteristics, and the idea is to make two measurements and combine them to eliminate the ghost. There are processing schemes that are based on the mathematics and the physics of the ghost, but I'm going to quote another famous geophysicist who's a friend of mine who said, you know, you didn't record it in QED. That means so you didn't record the frequencies in the ghost notch, and so there's really nothing rigorous that you can do about it. And we'll see today that that is simply not true. I used to be in this camp myself until I began to look at it from the wave equation point of view. And then there's a third approach, which is a hybrid scheme that tries to estimate a second measurement and then handle it in processing. Well, so what we're going to talk about today I call Wedge for wave equation deghosting, and contrary to what we've thought in the past, I'm going to show you today that it is possible to do a rigorous deghosting of single measurements, and in this case we'll be talking about P-wave measurements, but single measurements, not using two measurements, and yet rigorously take care of the ghost problem. I know it's thought theoretically that we needed two measurements, but we'll see why that is not true in just a little bit. So why another deghosting approach? Well, we've understood for a long time that there are a lot of benefits to towing the streamers deeply in a survey. And so we get a lot of benefits from that, but of course we'll see in a moment that the ghost notch becomes a problem because it eats right into the sweet spot of the seismic signal. Multi-component measurements are not widespread yet. A couple of service companies have offerings in this, but certainly not their whole fleet. And of course, we've got a lot of legacy data and legacy acquisition systems that will be out there for some time. And the other issue, of course, is that current processing solutions must somehow make an estimate of the missing frequency information. And we'd like to remove the statistical or estimation process and do it right if we can and bring in the physics of the problem. Well, so let's look at the ghost problem now pictorially, and maybe this is a little bit different from the way you've seen it presented in the past, but bear with me and you'll see why in a moment. So we think of an upcoming wave field in black, which reflects at the surface, comes back down to the streamer, which is the orange bar across the figure, and then they interfere at a certain recording time at the receiver, and this is what causes the ghost problem. Now, there's two special cases of the ghost that we always think about, and one is a certain frequency for the upcoming wave, and then the downgoing wave, at just the right tuning frequency, when they're added together, they exactly cancel each other. And this is the so-called ghost notch frequency. Theoretically, from this kind of development anyway, we would believe that we didn't record anything at that frequency, and it would have no representation in the seismic data at all. There's another special case, which is at half of the ghost notch frequency. Don't talk about this very much, but of course it also distorts the spectrum, and that at that frequency you actually get twice the response. And so basically the ghost takes the spectrum and alters it from the seismic source wavelet that we introduced into the Earth, and we'd like to take care of that effect. Now I'll show you this plot of the frequency spectrum, and this is what we're all familiar with. The traditional ghost model gives you these notches and peaks at the frequencies that I've just shown you. So what's the problem with the traditional ghost model? Why don't we just go ahead and solve this problem? Because after all, using a little bit of mathematics, we could, we all know what the ghost is. It's this exponential. So we typically write the total wave field as this ghost function times the upcoming wave field. The upcoming wave field is what we'd like to solve for, so why don't we just do that mathematically? Let's call it 1 minus g and take the inverse, and we could just solve that for the upcoming wave field. And well, how do we do that? You can write a power series approximation. Now the problem with doing this, of course, is that this inverse actually doesn't exist for some frequencies. In fact, if you look at it, this kz can occasionally be 0. That's what happens at the ghost frequency, the ghost notch frequency. And when that happens, of course, the exponential is 1, and so you're trying to divide by 0. So this inverse can't exist, and that gives you practical problems in trying to solve for an inverse function. You have to do some statistics away from the ghost notch to try to estimate it. And it also has another issue, which is that it ignores the ghost in the real world, which is a much more complex system than I just showed you in that simple cartoon. So let's just look for a brief moment at why the acquisition systems that make two measurements can be successful in eliminating the ghost. And there are a variety of ways of doing this. I'll just mention them briefly. An old idea that goes back to the 1980s is to have two cables that are over each other, one over and one under. And you can see the spectra in the bottom, the ghost notches are different, and you could imagine adding the two signals together basically to eliminate the ghost notches. There are other ways of doing this with, say, a sparse under situation where you only try to recover the low frequencies from the two deeper cables. And then, of course, there's the idea of slanting a cable, which gives diversity of the ghost notch all along the cable. And again, that idea goes back, in time, at least to the 1980s. And more recently, the idea of a multi-component cable has come along where you actually put complementary measurements into the cable itself. So you might have a hydrophone and an accelerometer, for example, or a hydrophone and a geophone, and then use the complementary nature of those to eliminate the ghost. We used to think this was necessary It's certainly sufficient to eliminate the ghost, but we're going to see that it's not necessary. Well, so what about the ghost in the real world? I said it was more complicated, so let's have a look at it. Well, again, we're starting with a picture of the cable at a depth D. The water surface is shown there. And the first thing I'll say is that, two things about the water. The velocity is not constant necessarily in the water, and the surface of the water is not flat and doesn't have a perfect reflection like we often assume. So there are a number of issues with this. I've just listed them here. Also the shape of the cable, both as I've shown it here in a 2D plane as well as in 3D, can vary. And so this creates a much different interference pattern than the simple one that we showed before. So you still might have an upcoming wave that then reflects off the surface, but now it's going to interfere with the other upcoming waves in a different way. It's very complex. It's going to depend on the shape of the cable. It's going to depend on the water surface characteristics. All of these things are going to make the ghost a little bit different from what we would have predicted from our original simple picture. Okay, so we've just seen that the ghost in the real world is a little bit more complicated than our simple ghost model leads us to believe. So now I'm going to take you through a little bit different analysis and derivation of the ghost, and we'll see that it's going to lead to a little bit different point of view on how we might solve the problem. So the way I like to look at this is by looking at the downgoing wave field first. And most people concentrate on the upgoing wave field because that's what we're trying to solve for. But let's just look at the downgoing wave field and make a few observations. So the first one is, if I ignore noise and I ignore things that are not part of the shot-generated upcoming wave field that I want to record, which is similar to what other deghosting techniques do, then I have to ask the question, how did I get a downgoing reflection? This is a little bit like which came first, the chicken or the egg. But I'm going to say if you have a chicken sitting there, you know the egg came first. And so we have a downgoing wave field. So we know that there had to be an upcoming wave field that first came up and was recorded on the cable and then reflected from the surface and generated the downgoing wave field. And this is a key point, in fact, the key point that we want to take away from this lecture. And I'll say the words in a moment that are most important, but let's look at another example. So we have another downgoing wave field, perhaps from a different location, arriving at the same time that we're focusing on, but it came from a different place because obviously it has a different propagation angle. So its upcoming constituent was at a different place on the cable and was at an earlier time different from the other one. So our downgoing wave field, of course, to get all of it, we have to sum all of these possibilities. And so we're going to make an observation that the downgoing wave field is some sum over over earlier versions, earlier times of the upcoming wave field. And of course, there's some amplitude and phase factors that we'd have to take into account. And I'm not going to get into that at this time because we're going to actually solve the problem in a different way. We're just talking about this to understand the physics and have a little motivation. So if you look at this, then what is most important to observe is that U, the upcoming wave field, is causal with respect to the downgoing wave field. That means that to have a downgoing wave field, you had to first have an upcoming wave field, and we're going to make use of that fact. So let's just look at this now. We have a downgoing wave field, the sum of the upcoming wave field. And of course, if we plot out what this trajectory looks like, it's going to be something very familiar to geophysicists. Okay, so what we've seen is that the downgoing wave field then can be written as the sum of earlier parts of the upcoming wave field. And as I said, you can calculate this trajectory itself quite easily, but let me just tell you, it looks something like an upside down Kirchhoff integral. So what this shows is that if we sum over, suppose we already have part of the upcoming wave field, and remember it's causal, so we will have part of it. So we do a little summation over the upcoming wave field, and then we're going to subtract that from the total wave field, and that's going to give us a new layer of the downgoing wave field, of the upcoming wave field, and then we can do the process all over again. So it looks like a Kirchhoff integral summed over existing values of the upcoming wave field, subtracted from the total wave field to give us the upcoming wave field. Well, now, of course, we could implement it this way, but I'm going to say that these are very small intervals that we're extrapolating over. So the last thing you want to do is to try to do a very small Kirchhoff integral. It's a lot of work. And anyway, I think we can do better than that. Once we recognize a Kirchhoff integral, we understand that the wave equation is at the bottom of all of this. So instead of doing it through Kirchhoff integrals, we're going to use a wave equation propagation, and I'll say a little bit more about that in a moment. But let me just show a picture of it to start with. So here's how the algorithm works. You have an upward propagating operator, and this could be like an RTM kernel or something like that. And it's going to take the upcoming waves, here shown in black, propagate them to the surface, and then we'll implement a reflection operator, which is going to reflect the data off the surface, and then a downward propagating operator that brings it back to the cable. And now at that point, we have recorded the downgoing wave field, and again, we can use the same idea we had before to subtract it out of the total wave field. So the main point of this is we use wave equation type processes. So for example, a finite difference RTM operator or phase shift could work. And the main point is that causality provides the initial conditions that we need to start this iteration. So let's just have a look at the mathematics for a moment. I won't try to go through this in detail. I'll refer you to our EAGE extended abstract, which has all of this, and you can puzzle over how many of the subscripts I have right or wrong in this. But it just shows exactly what I showed you pictorially there, that we suppose we're in the middle of this iteration, then we're first going to extrapolate upwards, and then we're going to extrapolate downwards, and then we're going to have the boundary conditions fulfilled that you see in equations 4. I think it's easier to understand, though, if I show you a picture of how the actual extrapolation works. So I'm showing now on the left side of the screen in black the upcoming wave field that I'm carrying along, and on the right in yellow is the downgoing wave field that I'm carrying along. So let's suppose we're in the middle of this iteration. Now the first step we'll take is to propagate upwards, and now we don't care what goes off the top of the surface at this point. And now we're going to implement reflection, and here I'll just assume that it was a -1, and so the existing wave field at the surface now becomes, the upcoming wave field at the surface now becomes the downgoing wave field with a change in sign. So we're going to propagate downwards, and now we're going to use the fact that we had reflection and fill in the boundary condition at the top. And now we have downgoing wave field at the cable, which we will strip off, and we're going to subtract it out of the existing total wave field, and that's going to give us a new set of values for the upcoming wave field, and we can start the process all over again. So this being video, you can run this back and forth a couple of times and convince yourself that this really is fairly simple. It's not the first time around for sure, but convince yourself that this is not a very difficult type of process to carry out. Well, let's now, after all the theory, let's turn aside and say, well, yeah, but does it really work? And so to test this, we're going to look at a shot gather from the familiar seam model. And you can see this is a shot gather from a very complex salt regime in the Gulf of Mexico. And what you see on the left is the input data, which is data that have been generated with a surface ghost. And then the panel in the center says deghost, and this is data that has actually been deghosted by the algorithm we just showed you. And on the right is what we modeled without a ghost at all. And so, of course, the two right panels we hope are similar, and so we'll just have a look at a little window first of all and analyze the spectrum, because we do see notches in our spectrum, and the first test should be, would this deghost in the sense of filling the spectral notches. And so basically you can see that the no ghost and the deghosted data are essentially overlays of one another, and have solved the ghost problem, and quite nicely, in fact. And of course, visually, we'd like to see this as well. So now we've subtracted the deghost and the no ghost and plotted it as the error. And so you can see it's quite small. There are a few artifacts on the right-hand side of the screen that you may be able to see that are related to boundary effects. And of course, this is being a wave equation process, you could expect some things like that to happen. Well, so we've just seen that wave equation deghosting can take a very complex shot record and fully deghost it. But now I'm going to move to a problem that I think is maybe pathological in a way, but I think will illustrate that wave equation deghosting is doing something quite different from other approaches to trying to deghost P-wave only data. So what I've generated here now is a monofrequency experiment. Now, our typical way of thinking about this problem is that a monofrequency, especially if it's taken at the ghost notch frequency here, 15 hertz for a 50-meter cable depth, in theory, the ghost model tells me I should record nothing. However, if you look at the left-hand screen, let me just walk you through how the ghost actually occurs. Then the upcoming wave comes up and we begin to record it as the monofrequency source information hits the cable. Then it reflects on the surface and generates the downgoing wave field. So I split these two apart here. And now when I add them together, you find that instead of recording zeros, as the ghost theory would predict, you actually record something else. You record the very first leg of the monofrequency, the plus and the minus troughs and the peaks, and then you begin to record zero. So this is a fundamental outcome of causality. If somehow we had an infinite vibrating source at a monofrequency, we would record zero, but of course, you know, there's no such thing as an infinite record in seismic. It's all finite records, and I haven't shown it here, but of course there's a similar effect if I were to truncate the source somewhere in the middle of the record. Here I've let the source go ahead and run longer than the recording time. So now if we look at this in the frequency domain, we get some surprises. So starting with the very faint dotted line at 15 hertz, we see this is what we would find from an upcoming sinusoidal wave field if it were infinite. This is what the ghost model predicts, essentially, a spike at 15 hertz and nothing else. But the causal upcoming wave field is different because it has a beginning and an end, and so that's the one that is again a line that has the ripples in it. And now if we look at the total sinusoidal wave field, which is the one I really want to concentrate on in green, then we see in fact it does not have a notch at the notch frequency as we would predict. And so formally, if we could get it right, we could invert this operator, and of course this is sort of a hand-waving proof that causality really does allow us to solve for even the notch frequency in an exact fashion. It's not a notch, it turns out. Well, so with this in mind, let's make a few observations now. First of all, causality, as I said, gives you more information than you thought you had. It's a more complex spectrum than the traditional ghost model would predict. It's not monofrequency. The total wave field and the upgoing wave field do not obey the classic ghost model. The notch is not zero, strictly speaking. And so you might wonder about data-driven deghosting approaches. They may be challenged by these kind of examples. For example, just take that single leg of the upcoming wave field and see if you can reproduce all of the monofrequency upcoming wave field. And having said this is all from a theoretical point of view. It's not really clear at this time what the implications might be for real data, and we'll investigate that in the future. So let's just review what I think are the advantages of approaching this through wave equations rather than through some sort of statistical means. Well, first of all, the method is pressure only. It could be implemented on land for geophones as well, but it's a single measurement only, no special acquisition. It exposes the physics of the problem, so we're actually modeling the whole problem. We could model the whole problem: variations in water velocity, variations in sea surface, receiver geometry, surface reflections can be complex. Anything that we can put into the wave equation, we can do with wave equation deghosting, and we can do it in 3D, which is important because not the subject of this talk, but we should always remember that the ghost is a three-dimensional problem. It's not two-dimensional as we generally develop it. There's no plane wave assumption here. We handle all the possible dips in the data, including in 3D, and we are able to give the correct spatial position for all propagation angles. We don't assume the traditional ghost model. There's no interpolation, statistical estimation, deconvolution, inversion in the classic sense, and so we just do it by the simple physics. But there are some practical issues, and so let's have a look at it. First of all, the physical parameters have to be known or estimated. You need to know the depth of the cable, the velocity of the water, the sea surface, etc., if you're going to do this. You need to be sampled well in 3D if you're going to do extrapolation. So the 3D cross-line spacing is still an issue. And so one might have assumed from the beginning of this talk that since we were able to deghost with a single measurement only, maybe we don't need these exotic systems. However, making measurements in the cross-line direction, say, for example, an accelerometer in the cross-line direction could be very beneficial in aiding to get a well-sampled grid in 3D. Very important. The one thing that we share here with all other ghost problems, as well as these first two issues, is the issue of noise. Noise as part of the wave field is actually handled properly here. So if you have some source that produces an upcoming wave field that then produces a ghost, it's handled here. You deghost the noise. However, noise not related to the wave field should be removed. Otherwise, you're going to have some issues, or account for it somehow in the algorithm itself. And a good example of that is a direct arrival. You need to handle that in a proper way, otherwise it's going to be a problem. You may have noticed that this algorithm is recursive, so you may have questions about whether it's stable. Our observation is it is in fact stable. However, when you add random noise to the problem that's not part of the wave field, you do see an increase in the noise values. And I would just say that all of these practical issues are things that other deghosting algorithms must address as well. So nothing really new here in terms of a showstopper for deghosting. So at the end of this, where do we stand? Let's talk about the conclusions and what sort of issues we may have to consider. We've shown that wave equation deghosting theoretically can perform rigorous up-down wave field separation on single measurement data. This is something we thought was mathematically impossible in the past. Now we've shown that in fact it is possible, and we just needed the correct physical formulation of the problem to be able to do it. Causality is the key, and I want to stress this again. I've said it before, but the observation that the wave field is causal, the very first reflections that we get in a shot are actually upcoming. We know that, so we can start our propagation using those first reflection values. Sensitivities are similar to other deghosting approaches. You have to know the physical model. It's going to react to noise in a very similar way. More importantly, we don't make use of a traditional ghost model. We just use the physics, and therefore we can bring in all of these physical parameters such as the sea surface, the shape of the cable, quite naturally in the process. The main questions that need to be answered now are how can we stabilize it, not stabilize it in the mathematical sense. It is a stable process, but I mean stabilize it for errors in the input wave field, such as the cable depth. You don't really know the cable depth a lot of the time exactly. You don't know the water velocity exactly. You may not know the reflection state of the sea surface and so on. So can you stabilize it so that it doesn't react in a negative way? And even possibly extending that idea, could we use this algorithm to actually invert for the physical parameters in question? That's a fertile area for further research. Well, I addressed this briefly before, but does it obviate multi-measurement streamers? Absolutely not. Even though we can do this with P-wave measurements only, there's some benefit, I think, to having measurements that are redundant in some sense. And one of the research directions we want to look at is how does this algorithm fit in if you have multi-measurements already? So that's a very interesting topic, I think. And so the future plans, well, we're going to look into that. How does it fit into the real world of deghosting and the fact that we now have multi-measurement streamers? But I'll just mention a few other things here. I haven't talked about source deghosting, but of course we know we have source-receiver reciprocity that we can use. And if you do this, wave equation deghosting then can be used to remove the source ghost in much the same way. The challenge there, of course, is that our sources are nowhere near as well sampled as the receivers. So we might only be able to do a 2D deghosting of the source with this, but that's an area for future work. And finally, I would just mention the FK methods. Maybe you feel I've been a little bit dismissive of the FK ghost model in the approach and taken there. However, if you check the abstracts from this year's EAGE 2014, you'll find a paper with my co-author Ralph Ferber on causal FK inverse filter deghosting, where we examine more the relationship in that power series inverse that I talked about and show that actually, even though that operator is not invertible, it's quite usable and can be used to deghost the data at the end of the day. I'll just leave that as a teaser. Come to the talk. It's on Thursday afternoon. If you missed the talk, check out the abstract on the EAGE website. Thanks for paying attention. I'm Craig Beasley from Western GECO, and I really enjoyed this opportunity to speak to you about deghosting.